Good morning, ladies and gentlemen. My name is Artur Gańcza. I'm from the Gdańsk University of Technology, and today I would like to tell you about the results of our joint research with colleagues from the University of York. We are investigating adaptive methods of identification of non-stationary systems with a mix of static and time-varying parameters. Such systems appear in different applications in underwater acoustic communication. One of them is self-interference cancellation in full duplex underwater acoustic communication. In full duplex communication, both communication devices can send and receive information simultaneously using the same bandwidth. As a consequence, the received signal from the far end transmitter is contaminated by the signal from the near end transmitter. The self-interference is formed by the transmitted signal that reaches the receiver directly and by its reflections from the bottom, the water surface, and nearby objects. This is why the recorded signal can be modeled as a mixture of the known transmitted signal convolved with the time-varying impulse response of the self-interference channel and the signal from the far-end antenna contaminated with the site-specific noise. It is worth noting that amongst these unknown parameters, only a fraction is usually time-varying. Those are the parameters corresponding to reflections from the moving water surface or moving objects in the underwater environment. The rest of the parameters corresponding to reflections from the bottom are time invariant. In our work, we use this knowledge about the nature of the self-interference channel to propose a high-quality identification scheme, allowing one to obtain reliable estimates of unknown parameters, which is crucial for self-interference cancellation. In this figure, we can see the power delay profile and maximum frequency of parameter variation of a self-interference channel, measured in the real-life experiment. Even though the amplitudes of time-varying taps can be substantially lower than the amplitudes of static taps, their high-quality estimation is crucial for securing reliable communication in the full duplex mode. One of the well-recognized methods for the identification of non-stationary systems is the local basis function method. It starts from the assumption that locally, inside some analysis window, parameter trajectories can be described as linear combinations of known functions of time, called basis functions. This allows one to use, inside the analysis window, a higher order but time invariant model. The estimation problem can be solved using the least squares method. The estimates of basis function coefficients are used to find parameter estimates corresponding to the central time instant. Then the analysis window is shifted to the next position and the estimation procedure is repeated. Such a procedure, although producing high-quality estimates, is computationally very expensive, since it requires updating and inverting a generalized regression matrix of large dimension at each time step. However, it turns out that under the assumptions listed above, the computationally simpler estimator can be proposed, which closely approximates the LBF estimator. This new method is two-step. The first step is called pre-estimation. It allows one to obtain estimates of system parameters that are unbiased, regardless of the type or speed of parameter variation. This procedure starts by computing the exponentially weighted least squares estimates, and later performs inverse filtering on them. As a result, we obtain estimates that can be regarded as true parameter trajectories contaminated with a white noise of large intensity. An example of such pre-estimates can be shown in these figures. Pre-estimates were depicted with black lines and the true parameter trajectories with red lines. This is why the second step consists of filtering of pre-estimates. Theoretically, any well-established filtering technique could be used here. However, when one uses the Savitsky-Golay filtering with the same set of basis functions as in the LBF method, then this fast LBF estimator approximates the original LBF estimator. This can be seen in these figures. Here we see parameter estimates presented with black lines obtained using the LBF and FLBF methods. They are superimposed on true parameter trajectories shown by red lines. As you can see, the FLBF method can provide estimates almost indistinguishable from the LBF estimates at a substantially lower computational cost, which can be made even lower for properly chosen basis functions. Another advantage of using the FLBF method is that it allows one to process each parameter trajectory separately. Thanks to that, we can apply Savitsky-Golay filtering with several basis functions for time-varying parameters and the averaging filtering for time-invariant ones. This is equivalent to using the mixed-mode model of parameter changes, in which we assign one constant function to time-invariant parameters and several functions to time-varying parameters. In practice, we don't know which parameters are constant, and we cannot expect that they will be globally time-invariant. So the question remains how to determine which parameters are locally time-invariant. For this purpose, we use the well-known sign change test. We note that if the trajectory is locally constant, then the sequence of residuals can be regarded as a realization of zero mean white noise. In the upper plot, we can see the real part of residuals for a time-invariant parameter, and in the lower plot, for the time-varying one. Hence, if the parameter is locally constant, residuals should change their sign on the average every second sample. This observation is reflected by our null hypothesis. If this hypothesis holds true, residuals obey almost binomial distribution. This means that we can easily set the threshold for the minimum number of sign changes of residuals inside the analysis window, after choosing a suitably low probability of type 1 error. Therefore, we accept the null hypothesis when the number of sign changes is above our threshold, and we run this procedure for both real and imaginary parts of residuals. If the null hypothesis is accepted for both of them, we regard the parameter as locally constant. Otherwise, we regard it as locally time-varying. Please note that this procedure is computationally very cheap, since it involves only operations on the signs of residuals. Our second improvement to the identification scheme is based on the observation that the FLBF estimates tend to lag behind the true parameter trajectories. The reason is that pre-estimates are only approximately unbiased. In fact, they inherit some delay from exponentially weighted least squares estimates. Since this delay depends on the frequency content of each parameter trajectory, an adaptive procedure for delay cancellation is required. To debias our final estimates, we run several filters with different delays, and at each time instant we choose the one that minimizes the local sum of squared interpolation errors. The delays are chosen from the interval centered around the nominal delay that can be calculated when we assume slow parameter variation. All of the proposed techniques were tested with signals recorded in a lake experiment. In this experiment, we were using only one transceiver equipped with the transmitter and receiver. In this situation, self-interference is the only signal recorded by the receiver, which allowed us to measure the effectiveness of self-interference cancellation using the self-interference cancellation factor. The initial signal to interference ratio was close to 60 decibels. The lowest curves correspond to FLBF method using several basis functions for every parameter. Above, we have the results after applying the original LBF method. Finally, the best self-interference cancellation was possible after applying the FLBF method with an adaptive choice of time-invariant parameters and adaptive debiasing. For comparison, we also present the best results that we were able to obtain using just the exponentially weighted least squares algorithm and the state-of-the-art time-updated recursive least squares algorithm. As you can see, our new method can improve self-interference cancellation by 7 decibels compared to these two methods, and by 2 decibels compared with the LBF method. Thank you for your attention.